So lecture 14, system of linear equation and generalized inverse. So we already discussed on system of linear equation in previous classes, a very fast in lecture 2 or 3, but we'll discuss here slightly in deep, because in the previous classes, in the first half of the class, I think it's a lecture 1 or 2. No, not in the 4, 5. There we do not introduce the idea of rank and this vector space thing and this column space, row space. Now we will see this system of linear equation in light of rank, row, column space, and this rank nullity theorem, nullity and linear transformation. So what is system of linear equation? Brief recapitulation. So it's just we can think this as a matrix form. We know this is in the matrix form Ax equal to B, where A is some matrix n cross m. This M cross 1. This is B equal to M cross 1. So it is a number of equation is n. All are linear. There are m variables. So x1, x2, xm. M variables, n equation. This can be written in this form, matrix form Ax equal to. Now, what is homogeneous? If B equal to 0, then it is called homogeneous. If null matrix, and if B equal to not equal to 0, then we say it is a non-homogeneous system. Consistency, if there exists some x for which Ax equal to B, then we call it is consistent. If for all x, if Ax equal to not equal to B, then we call inconsistent. Now, what is the solution? Solution space means it's a set of all such x in Rn or in any field. If we take any field Fn, this is called solution space. So we know this solution space, if it is for a homogeneous system, the solution space is a subspace. It's a subspace. This is a subspace. Sorry, it's homogeneous. So it's a subspace of F. It is clearly we can. It is trivial to see that this is subspace of not only the subset is subspace. Now, if it is non-homogeneous, it can't be a subspace because 0 is not there. So 0 is not there. That's why it can't be a subspace. Now, system of linear equation, you can think like that. So if we know that is a matrix. Matrix is if there is a matrix A, there is a corresponding linear transformation from, say, okay, Fn, in general Fm to Fn. A is n cross n. Then it is Ta of x equal to just Ax. So that means actually equations. We know what is the relationship between equation and the function. Sometimes it's a functional equation or a quadratic equation. Ax squared plus bx plus c is equal to. This is called equation. But the idea is you just think as a function. Ax squared plus bx plus c, and think the solution of this fx equal to 0. That means we just have a curve fx, f, and we take the solution. That means intersection with the x-axis. The similar thing here. So when you talk on this equation, we actually don't see it like an equation. You should think like it's a function. So it's a function Ax, function x goes to Ax. So this is a linear transformation, and we actually want to find the all x as the Tx equal to 0. Tx equal to 0. So that means it is a kernel. Is a kernel of T. So is the kernel of this linear transformation is the solution. The solution is nothing but kernel of this. So you can think it's better because actually this equation has actually no meaning. We know the function has a meaning, but equation actually is slightly ambiguous. What is equation? If I ask what is equation, there is actually no definition of equation. So think like that. So for a matrix A, there is a linear transformation corresponding to the matrix A. and we want to find the kernel of this. So kernel of this linear transformation is a solution space. So that means we have to find whether this kernel is a phi set. If it's a phi set, that means inconsistent. If it is not a phi set, there is a consistent. If it is a one is singleton element, obviously it's a kernel is a for this homogeneous system, kernel cannot be phi because null vector is always there, so it can't be inconsistent. Then whether it is a just a singleton zero vector, or it is a whether its dimension is the question is whether the dimension is 0 or greater than 0. If the dimension is 0 is a unique solution, dimension is greater than 0, it is an infinite solution. And infinite solution you can classify it just like a dimension. So is no solution, one unique solution, infinite solution. You should not classify the solution like that. You should classify such a way that consistent and inconsistent. If it is consistent, what is the dimension of the kernel space? That's the two questions. Whether it is consistent or not. If it is consistent, what is the dimension of the kernel space? If for homogeneous, it is always consistent. Now, question if for it is non-homogeneous, so there is no question of kernel. The kernel is not the solution. So what we'll see in the next slide what happens for if it is inconsistent. Now, so consistency and column space. So what is the consistency? Actually, is the column space. Now we know this is if I write this, so that means if some x exists for which x equal to b, that means b is just a linear combination of the columns of A. It's basically the linear combination of columns of A. It's just a linear combination of columns of A, because we can easily see that this term is always multiplied with this column. So that means this b is nothing but this x1 into the first column of A plus x2 into the second column of A, that xm into the mth column of A. So that means the b is the linear combination of it. So the question is consistent or not? The question is just is the b is a linear combination of the columns of A. That means whether b is in the column space of A or not. If b is in the column space of A, that means b can be written as the linear combination of columns of A. That means this is the x is. You just take a b and you find what is the linear combination of what is the b in terms of the linear combination of all the columns of A, and collect all this coefficient, and this coefficient give the x. Now it is clear if this all the columns are independent, is a full column rank. Now it is clear if it is a full column rank, then this is unique. If it is a full column rank, this representation of b, the column b, is actually unique in terms of the column of A. So that means this solution is unique. So that means it is clear that this solution is unique. It is exists if it is in the consistent, then it is exist, and if it is all the columns of A are independent, then it is a unique solution. Now, if all the columns are not independent, the columns are not independent, these columns are dependent. That means this coefficient that all x1 the first column plus x2 dot 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 dot. This representation is not a unique representation. We can several ways we can represent this. So that means there is infinite solution. If it is more than one solution, this must be infinite solution. If f is infinite for R, if field is finite field, then there is no question of infinite solution. Always the solution is number of solution is finite because the field is finite. So actually, this infinite solution, finite solution, this thing is actually very vague. It is true for C or R. But in general vague field, you have to actually ask whether it is a dimension is 1, 2, or 3, something like that. So again, this consistency, it is clear that this is consistent if this B is a linear combination of it. That means if you just append this B with A, it is a m cross n, right? N cross 1, it is m cross 1. So you can append this. It's called augmented matrix. Sometimes write like a partition thing. Now, this B, this column B has no fresh contribution over all these columns, n columns. So all number of independent n columns. So rank of this column space is same as rank of this column space of AB, because this B, that column B, that new vector, actually has no new contribution. This B can be B is a linear combination of all these columns of A. That means is consistent if and only if this rank of this is same as this rank of A. So obviously rank of A is always less than or equal to rank of AB. This is clear. Now if it is equal, that means if rank is equal, that means B has no new contribution. So B can be written as a linear combination of all the columns of A. That means there is a unique, there is a solution, may not be unique. And otherwise, if there is a solution, then B can be written as a linear combination of the columns of A. That means the rank is same, because there is one way always, because it can't be less. The rank of A B cannot be less than. So consistency, the proof is clear. The consistency of the system is just rank of AB is rank. Now, since for homogeneous B is 0, this is just rank is always equal. Now again, unique and infinite solution. Now it is clear that unique if is a full row rank, a full column rank. This A has full column rank. All the columns are independent. The set of columns are independent. So if it is a full column rank, then this is a unique solution. Not only for this homogeneous, it is also true for homogeneous, non-homogeneous both. So now if it is a square matrix, A is a square matrix, a full column rank, it is a full rank. So that means it is a non-singular. But if it is a not a square matrix, now the consistent unique solution means there is a full column rank. Now, if number of column is more than number of row, that means number of variable is more than number of equation. That means number of row column is more than number of row. Now, then it can't be a full column rank, because the column rank is same as row rank. So if it is 4 cross 6, so 6 variables and 4 equations, it can't be ranked can't be 6. It's always less than or equal to 4, minimum of the number of row or number of columns. So it can't be a full row column rank. So if there are more variables than equations, it can't be a unique solution. Can't be a unique solution. Either no solution or is an infinite solution. So this uniqueness thing is coming from the dependency and this independency of the all columns. Now coming back to the solution space. Again, what is the dimension of the solution space for is a homogeneous equation? This is a question. So it is actually the dimension of the solution space is a subspace of the FM. So this is the question whether the dimension is 0. If it is 0, the unique solution, and if it is a non-zero, then it's the infinite solution. It's always consistent. Now think this is a linear transformation, and this is actually the kernel of this linear transformation. And for the rank nullity theorem, what do you see? On the rank, if it is a m cross n, we write m cross n or n cross n. It is m cross n, right? Now it's clear now. So number of variables of n. So from rank nullity theorem, what happened? So we know that rank of A plus the kernel of this nullity, actually nullity of A, this must be equal to n. This must be equal to n. So rank of A plus nullity of must be equal to n. Now it is clear rank of A cannot be greater than equal to. It cannot be strictly greater than. It may be equal or it may be less. That means nullity is greater than equal to 0. Obviously, this nullity is greater than equal to. It can be negative. So the question is, if rank of A is same as n, that means the nullity of A is 0. That means nullity of 0 means it is only 0 is the only thing. So unique solution. And the rank of A is not equal to A is strictly less than n, then is infinite solution. Infinite solution for the infinite field. For infinite field. For finite field, it can't be infinite. So this question of nullity is strictly greater than 0. So consistency actually came from this number of independent columns, whether it is a full column rank or not. Now, this is not no use of that number of variables. Consistency, inconsistency, there is no use of n. We don't need what is n. But for uniqueness and this, or unique or non-unique, not unique, then n is involved now. So kernel of the linear transformation and solution space. We already see this kernel of the linear transformation is the same as the solution space, basically the kernel of the linear transformation. For solution space for the homogeneous system. Now, question, if it is not homogeneous, what again? Now, all we know, if there is a corresponding, it is called reduced system, and if there is a solution, is a nullity of this, say. So any vector from null space, this null space, n is the null space of A. So any vectors from the null space of A is actually solution. This is a solution space. Now, if there is a solution, if it is a consistent, if B in the column space of A, that means there exists a solution, say U belongs to that Fn, number of variable is n. So such that AU equal to B, we have this. Now, clearly, this solution space of this is just the flat. This is a V vector sum this null space. So this is a flat. So that's the flat is important. So solutions of this all non-homogeneous system is a flat. You can easily see like that. If something is solution for a homogeneous system is this, it's just a shift with V vector. There's a V vector, there's a V vector, then there's a shift of this. And this is the flat. We know this is flat. So some vector plus non-zero vector plus a null space, a subspace is a flat. So now null space is a subspace. So V plus, it's not B, sorry, it's U. It's U. Let's see. It is clear, it's trivial. If you take any from null space, say x0, then U plus x0 is A of U plus x0 is AU plus AX0, x0 is 0, AU equal to B. So it is. So this is a very important thing. So this flat is actually the solution. Now there is a same idea of the dimension on the flat. Flat is not a subspace, but the dimension, we can think the dimension of the flat is the same as the dimension of the null space. So now it is clear for non-homogeneous system what will be the infinite, finite, and no solution. It is clear. Say first of all, if rank of A is strictly less than, it can't be greater than the rank of A augmented matrix, then no solution. There is no solution. If this equal to this, there is a solution exists. But if it is exactly equal to n, we already see, then the nullity of A is 0, so it is a unique solution. And if it is a greater than n, sorry, it can't be greater than n, sorry. If it is a less than n, this is just equal and less than n, there is an infinite solution. So this result we actually know from the school, but the proof is here. So proof is not tough. It is really trivial, basically. Once you have the idea of this thing, this nullity and this rank, all this thing, this is basically trivial. But I think the most important and most magical thing in this proof is that the B is nothing but a linear combination of the rows of columns of A. That is the most beautiful thing to observe. That actually we don't observe, we never observed in our school. When in class 12 we deal with the system of linear equation. In no books or nowhere it is observed that this B is a linear combination of the columns of A. Once you observe that the B is a linear combination of the column of A, everything is now very much straightforward. So this is the solution space and the connection of all these things. Now, what is if a system linear equation is an infinite solution? That means what? That means some equations. Sorry, if there is a more equation than variable, Maybe some equations are, maybe may not be more equation. Maybe there are say 6 variable, 3 equation. Maybe out of 3, the third one is just a linear combination of the rows. Now, previous slide we just talked on the linear combination of column. Now we are talking on the linear combination of row. So in matrix A, if some rows are the linear combination of the others, that means this equation, that equation corresponds to that row. If the 6th row, the 6th equation is just redundant. Redundant means this equation has no extra information. So we just throw out this equation. We can just throw out and this equation and reduce number of rows. So if the 6th equation, the 6th is the redundant, that means the 6th equation can be written as the linear combination of the other 5. Then throw this 6 and you have only 5. So the number of column will be reduced. Now this is called redundant equations. So redundant equation is the equation which can be obtained the linear combination of the other equation. Now obtain for the other equation not only for A, the question of B also there. So if A is this and B is there, number of row of A and B is same actually. If some last row or any other row, if this is a okay, the last row is a linear combination of the other row, say, and if such a so happen that this thing is the last element is not the same linear combination of the other thing. That is, if you just put together A and B, if you put together A and B, then the last row is this is A, B. Now, if so happen that this last row is not a linear combination of the other, but this row is a linear combination of this other rows, remaining rows, then it is actually inconsistent. That means it is actually inconsistent. This system will be inconsistent. Because if you just use some suitable row operation, you can put 0 there, but in the last row there will be 0 because they are not a linear combination. So that means from what is the rank of A, there is a one extra rank for AB. So one more extra non-zero column we have. So that means for the solution exists, then this redundancy, the redundant in the equation means not only the redundant in terms of the rows of the A, is actually dependency on the in terms of the rows of AB, the augmented matrix. So if any row which is a linear combination of the other rows in the augmented matrix, then the equation is just a redundant. And if it so happen that okay, there's a row of A which is a linear combination of other rows of A, but that corresponding row of AB, the augmented matrix, is not a linear combination of the other, then this is an inconsistent equation, inconsistent system. Now, if you go to the echelon form of the system, we know that if you have apply a linear elementary row operation on the whole AB, not in the A, maybe, then this system of equation will be changed, but the system is equivalent. That means that the solution space is not changing. If you apply the elementary row operation, then solution space will not change. Solution space will be same. Now, once we have a echelon form of this matrix, that have a echelon form of the system also, and what will be that? That means if somewhere the reading 1 is there, all are 0 above 1, something like that, and 0 rows are there. So if it is a B, that 0 row must be contained 0 also here. If it is not 0 row for A and there is a non-zero, that corresponding row is non-zero for AB, this again is inconsistent. So there is some 0 rows there. Now this is the echelon form. Now once you have an echelon form of this system, now this we know this is the same solution for the initial AX equal to B. Now what is the advantage of this echelon form? How do you, now if it's always 1 is here, so you start with 1 here. May not be 1 here, it may be some 0 column may be there. because you can't change the column, so maybe zeros. Yes, some zeros are safe in first. Now, in first some zeros, what is the meaning of that? That means this variable x1 is a free basically, because in the equation x1 is not involved. In every equation, in some columns are zero column, that means that corresponding that x1 is free. This is called free variables. You can choose any value of this x1. So that is a free. Now, if there is any column with zero, all the zero column, the corresponding variable, because the columns actually correspond to the variable and rows correspond to the equation. The corresponding variables are free. Now, some free variables also there. Say this is 1, 1. Now what? Now, if I say 1, 1 is the leading one. Now all those are 0. Now what is the equation? In equation, you will see only one equation involved x2. Only one equation involved. So leading one, for the column is 0, that corresponding variable is nowhere in no equations. Corresponding to the leading one, that column, the leading one where the leading one exists, that column actually corresponding to that random that variable, we see only one in that variable in the only one equation, the corresponding row. Then again some maybe say 2 here, then maybe some 0, 0, 0, 0, then again this is the leading one. The leading one, then you will see that the x4 is the only in the second equation, nowhere the x4 is. That means the three type of now variables. One type is that does not occur anywhere, so it's a free, you can choose anything. There is a variable where exactly in one equation that variables are occur, and the rest are in several equations. That means you just then what you will do, you will just that variable which are in the only one equation. Say x1 is in the only one equation, then you just write x1 here and you just put the other variable in the other side. Similarly, x2, you just put the other variable in the other side. It is not x2, it is x4. Sorry, it is x2. So now in the echelon form, the system will be looking like that. Some variable are absent in the system, and some variables which is some x2, x4 equal to x2 equal to something. With that something in the right hand side, some variables are there, and left hand side there are some variables are. Interestingly, left hand side the no variable is repeating, and this left hand side variable nowhere in the right hand side. And in right hand side some x3 is there, x3 may be there. Now you just choose this right hand side variable freely, and you will find this x2, x4, that variables. And you have a free choice of this x3, x4, x5, because you can this x3, x5 other thing, because this variable is not in the left hand side. So this will never give the inconsistency. You just put any value of this. Nowhere inconsistency will be there. Just put any value of this right hand side variable, you will get this corresponding this variable, because this always every equation actually for standing for this x2, x4 this in terms of the other, and the rest you can choose anything. So that means the free type is actually that where these equation variables are not involved, and these variables in the right hand side, these are also free. The ones are not free, this is not free. Obviously, you can change this. You can, if you put x3 here, x2 in that side, in that case x2 is free variable. But there is a problem. If you take x3 is this side and x2 is this side, then x2 is your free variable. Obviously, x3 is not. But this x3 have involvement of here also. Then you have to put from this value. Then again, from that x3 you have to put here. But here is independently you can just calculate all these variables. So it's the easiest way to find the solution. This form is the easiest. This is the simplest form to if you want to find the solutions. So if you write, you write the solutions like that: x3 equal to c1, x5 equal to c2, any variable, any number. If x1 is not involved there, so x1 is any number. X2 is some 3c1, c2, 3c3 or something minus 5 x7 like that. So this is idea of PFL, and this idea is coming from this echelon form. It's very interesting in the very useful for the solution purpose. And now there's a short brief introduction on generalized inverse. What is this? We know Ax equal to B is a equation, and we know how to find, there is several methods to find Ax, but there is one method. If A is a non-singular matrix, we can always find A inverse without knowing what is B, and then we just find the solution as A inverse B if A is a non-singular. But if so happens it is not a square matrix, or it is a rectangular matrix, if it is square matrix but still the determinant is 0, then whatever. Then we have an idea of G inverse. We can still find a matrix G such that your this AGA is equal to A. If you find such a matrix G, A is given to you, such as AGA equal to A, then G is called G inverse of A. And in that case, if Ax equal to B is the equation, obviously if it is singular, non-singular matrix, the G inverse is unique, and that G inverse is the inverse of the matrix. And you can see that G inverse exists, G inverse is unique, then it must be, the A must be so non-singular, because the converse also true. And this has a solution. The solution is X equal to GB. And the equivalent condition is there. This is the one thing. The third one. The equivalent condition is AG is idempotent. That means AG square equal to AG, and this and rank of AG equal to A. We know rank of AG is always less than A, strictly less than or equal to A, maybe strict less than, but if it is AG equal, rank of AG equal to A, and AG square equal to AG, then this is equivalent actually. And one more extra AG is GA is in idempotent. GA square equal to GA, and rank of GA equal to rank of A. If there is one of them occurs, then the other three occurs. So you have to check whether AG is idempotent and whether rank of AG equal to A or not. In that case, G is the G inverse. And what is the utility of G inverse? G inverse to find the solution. Now, it is clear that G inverse is not unique, because say if null matrix, sometimes it's called G is right as this. If it's a null matrix, then any matrix which is a compactable. So AGA is the defined that proper order, that any matrix of the proper order is G inverse. G inverse. We're not going to go through the proof. You can see in the Rao Vingashankaran. And again, this system will be consistent if the G inverse exists. If the G inverse exists, then it is if and only if the subsystem will consistent, the G inverse exists, and G inverse exists, clearly by the definition, this is a solution. Solution exists. And actually, there's an infinite many G inverse. If it is not unique, say again, it's infinite means for Rn's or any infinite field of infinite order, infinite elements. That the thing is actually you can find the general solution also. A is equal to this, and if you have a G is G inverse of A, G is G inverse of A, G inverse of A, then what are the solution? What are the solutions? You know the 0 is the solution, but you can find from this G inverse G0 is 0. So we know that 0 is a solution. So this does not help you. Ax equal to B, the solution is X equal to GB. That does not help you, because you will get the 0 there then. And 0 is a solution. It's no need of G inverse. So all the solution, all the general solution of this equation is then GB. Oh, sorry. Sorry. If G is the G inverse of A, and all the solution of this is not GB, sorry, it is just I minus GA into Z. Z is any vector, arbitrary vector. Z, you can take any vector. So you just find I minus GA, take any vector Z. These are the all solutions. And for Ax equal to b, the solutions are that one solution is a GB plus that the other solution, the corresponding homogeneous system. So that's all for this lecture. A brief introduction on G inverse.